Hello, everyone. My name is Michael Yuan, and I'm the CEO and founder of a company called Second State. We do software performance engineering. Welcome to my talk. This is my home office in Austin, Texas during the pandemic. And I hope you enjoy this talk, and I hope we can meet in person soon. So let me start sharing my screen first. Let me move myself to the corner. Okay, present. Okay, so here we go. Well, the topic of this talk is performance engineering for application developers, especially web application developers. So when this topic came up, a lot of people ask why, because for many years, the main challenge of web application is not performance. That is very evident with the rise of frameworks like first with Java and with Ruby on Rails and with JavaScript on Node.js. All those frameworks are not known for their performance. They are known for their productivity, developer productivity, ease of use, and all those other features, safety, and all those other features, just not performance, right? And over time, they get optimized a lot. But when they first came out, most people would say those are slow languages. When Java first came out, it's definitely a slow language. It has a reputation for that, right? When Ruby first came out, when JavaScript was first used on the server, it's the same reaction. And people typically have two answers to that. The first answer is what we call the Bill Gates answer, is to say, yes, I know it's kind of slow, but technology evolves so fast. So in 3-4 months, it'll be fast enough. Oh, well, that's actually the answer Bill Gates gave when people criticized that the Windows software is too bloated. He basically said, the CPU for computer is evolving so fast. So what's slow today is not going to be slow tomorrow. So why spend all this time, optimizing things that are going to improve on itself, right? Why wouldn't you spend time that's optimized for user experience and features and other things that are going to have long-term value, which I thought it worked really well for them, or for him and for Microsoft, right? The second argument is, oh, I'm just writing a web application. That's the application. All the application does is babysitting a database. So someone coming a request, I go to the database and fetch the answer back to them. That's that use case. It doesn't need a whole lot of performance, so to speak, right? So that'll be the second answer. I don't need it. The first answer is going to improve by itself. The second answer is I don't need it. But I think things has changed in the past couple of years that forced us, forced the entire industry to have an entirely different look at this whole problem. So I referred to an article that published on the journal Science only a couple months ago. Those are top computer scientists published this article. And from the title of this article, you can get a hint. There's plenty of room at the top of the stack, right? Because 40 years ago, Intel's Gordon Moore wrote an article called "There's Plenty of Room at the Bottom." The bottom of the stack is what? Is the hardware, the CPU. What Dr. Moore meant is the CPU and hardware are going to continue to improve at a rapid pace. So everything else going to lift with the tide, right? So you don't need to spend a lot of time optimizing software. You can spend a lot of time optimizing software in terms of its developer productivity, the human productivity, not the computer productivity. Because what's slow today going to be fast enough 3 months from now. So that's what we refer to as Moore's law. That's basically driven the productivity improvement in the entire computer industry for the past 40 years. So that's essentially the first argument I just gave, right? Is that yes, it is slow, but it's going to improve. However, this article talks about the Moore's law has stopped. As we all know, the computers and hardware are not really getting faster. The clock speed is definitely not getting faster. It's the size of the transistor has gone down from, say, 10, has gone down a little, but not a lot, right? So the way to get it faster is to do like GPU or add more cores to do more parallel computing and things of that nature. It's not the raw performance is improving. It's you throw more computers at the same problem, right? So so that's perhaps that's one of the biggest challenges that's the developers today going to face. That's did not really exist in the past 40 years. That's a completely new problem that people are going to have. And then there'll be the second problem is to say, okay, yeah, it's maybe not getting any faster, but all I do is database. That's primarily limited by the network bandwidth and hardware and hard disk speed. That's and if there's more requests, I can just open more servers. There has been a lot of study in terms of server horizontal scalability of those services. So we can do sharding and we can do a lot of things. So so why performance is so important? Well, that is because another thing happened in the past 5 years when Moore's law stopped is on the software side, we have figured out how to utilize more and more computing power, especially with the emergence of, say, artificial intelligence, deep learning. And all those applications require a huge amount of computing power that is previously not available. And in order to incorporate those features into your application or into a web application that you are building, that is not just database, you would actually need to care about performance. As we'll see later in this talk, there's a huge difference in terms of the software stack you choose versus the performance you're going to get. So here is the figure one in this in the science paper, right? So how do we? So hardware has stopped improving, but the demand for computing power has gone up. What's the solution? So the leading computer scientists give us the answer. They said there's plenty of room at the top, meaning today's software stack has a lot of inefficiencies that we can squeeze out by doing software performance engineering. Like I said, that's what my company does, right? That's why I'm giving this talk, right? So it's removing the software bloat and tailoring software to hardware. We have new hardware that's designed for specific problems, like for deep learning and for for things like that, or even for Bitcoin and for blockchain. There's special hardware being developed for that, and to tailor software for that, not just to have generic software that's designed for CPU to access those hardware. So by combining those, if you read this paper, the paper showed a Python program by rewriting it in state-of-the-art C++ and running on custom hardware, you can get a performance gain of 4 orders of magnitude. That's over 10,000 times performance improvement. So that's actually also is something that we have seen routinely by when people have a web application that does database stuff. They don't do AI not because they don't want to, but because they can't, because the software stack is not efficient enough to support this type of compute-intensive applications. And by changing the software stack, we would be able to squeeze a lot more performance without changing the underlying the CPU. We may need customized. Sorry. We may need customized software. We may need customized hardware to be in the mix, but not more CPU power, because CPU power is not improving anymore. So let's see a case study or example in action. Okay. So the goal here is to create a cloud application that runs TensorFlow inference on an image. That's I think that's the use case a lot of people have considered, right? I have a web service or web application that would take an image and then run a TensorFlow model. There's literally hundreds of thousands of TensorFlow models trained for different purposes on those images, on this image, to do things like facial recognition or object classification, anything you can think of. So this is a typical use case, run TensorFlow inference on the image. So depending on the software stack that we use, so if we implement this TensorFlow inference metrics on, say, JavaScript, and even run this JavaScript in a very efficient runtime. So for instance, in the WebAssembly runtime in V8, in the interpreted mode, meaning the JavaScript running as the way it's supposed to, as the way it's designed, as a scripting language. We are looking at 10 minutes of time on a state-of-art CPU to process a single image. Okay, 10 minutes. That's clearly too long for web application. It may be okay for, say, a asynchronous function of the service that you need to, it's asynchronous. So there's plenty of time on the back end to process those things. But 10 minutes for waiting is clearly not good enough for web applications. So now we rewrite it in TensorFlow.js in just-in-time WebAssembly. So that's not in the interpreter mode, but TensorFlow.js is TensorFlow's C library cross-compiled into JavaScript or WebAssembly through the EMCC compiler. And it runs in the V8 WebAssembly with a just-in-time compiler optimization. That speed up significantly because that allows the application to be compiled and run instead of being interpreted. That alone creates 500 times performance gain. It's reduced from 10 minutes to around 2 seconds. 2 seconds, I think it's fairly acceptable for web application now, right? That's because the time you need to do the network transmission and all that is in the order of seconds. So 2 seconds is probably good enough for the single interaction like this. However, if we optimize our WebAssembly stack, it's not even go to native, but do WebAssembly with ahead of time optimization. For instance, the SSVM called second state VM is a WebAssembly, open source WebAssembly implementation that we have. To run the same application, you can get to half a second, which is 4-time performance improvement again. That's half a second, I think is very acceptable to most, I would say, interactive web applications, right? But you can optimize it even further by giving it custom hardware like GPU, and then have the compiler optimize instructions for GPU. You can get another 10 times performance gain. So it now goes to 0.05 seconds or less per image. If you think about that pretty much allows you to process real-time video data, because real-time video data is about 30 frames per second, right? If you want to recognize every single face on every frame of a video image, of a video stream, you can more or less use this now. That's can you do 30 frames per second? May not, but you certainly have the capability to do. But you can sample it to do like once per, do one recognition for every 3 frames, something like that, right? So to do that type of performance allow us to actually do streaming video and run AI application on top of it. Then, of course, you can have full native, meaning that you don't use WebAssembly at all, that you just write the code in C, C++, and then run on bare metal GPUs. And that would cause it to be even more performant. That would be under 0.05 seconds. So that's the range of things that we can see. So we can see from JavaScript being interpreted JavaScript to precompiled WebAssembly. That is basically in the same family of technologies, because WebAssembly evolves from JavaScript, right? Same family of technologies, and we already got 4 orders of magnitude improvement in performance. So that means that I agree with the science authors. There's plenty of room at the top. And in this talk, I want to give you some real examples and tips in terms of how to optimize for your own application. Right? All right. So that's the thing. It's there's a saying to say it's turtles all the way down. What is the world being built on? As we have looked at, we have just mentioned, things like JavaScript on Node.js, when it first came out, people say the performance is not good enough. That's you guys really need to improve performance. So fine, let's improve performance. And now most people who use Node.js would think it performs pretty well. That is because Node.js fundamentally is not a JavaScript framework. It is a JavaScript runtime that built on a C++ engine. So the Google V8 is completely written in C++. And most of the common tasks you use in Node.js, like the file system operation, like the image resizing, And you know, those compute intensive tasks, they are all written in native modules in C++. It's just providing a JavaScript as the interface for developers. So what we would argue is Node.js achieved high performance today, not because it's a JavaScript runtime, it's despite its use of JavaScript. It's most of the heavy lifting is done by native code, native machine code in C and C++. The same thing happens in Python. You know, if you do heavyweight machine learning and AI applications, you often use Python to write your application. But you are only using Python as an interface. So all your Python codes actually get translated into native modules. They run it natively in OpenCV and in TensorFlow. All those libraries and modules are written in C++ and compiled to machine code. So the trend is become very clear here, you know, is that we need something for developer productivity, you know, JavaScript, Node.js, Python. But on the other side of the things, we need something that is high performance, which is translate everything into native binary code. And for most applications that application developer develop, they sit in the middle, you know, so if you write a complex Node.js application, a lot of your logic can be executed in JavaScript, and some of them, you know, like you know, image resizing or file operating, like the things I just mentioned, would have gained from the high performance of the native modules. But the more application logic you have in your application, the more business logic you have in your application, the more JavaScript you're going to use, and the more JavaScript you're going to use, it's slower it goes. So for most application developers, it's a balance between those two, right? You know, that's for very simple applications, I can achieve really high performance because mostly all I do is to call the APIs in Node.js that get translated into native function calls. But as my application grow more complex, as I'm an enterprise developer, you know, if 80% of my logic is actually built in JavaScript that has no corresponding native library, then you can expect the application to run pretty slow. So I think that's one of the challenges that you know, more and more developers are finding out. You know, is to say Node.js or Python is really performant if you follow the tutorials. But if you write a ton of your own code, then performance engineering become a really big problem, right? You know, so that's a problem that's we think, well, you know, at least I think, would be more of a problem for future developers. So because of all that, you know, that's we have seen, you know, the Moore's law is not holding, and the demand for performance is great. And by choosing different frameworks, you can achieve vastly different performance results. And most of the frameworks today actually go with the route of having a high-level interface and then do the actual computing as native code, right? So that's how we define great performance, is to follow the lead of what Node.js and what Python has done in the past. You know, is that on the performance side, we only have one requirement, is it should be as fast as a native library. You know, so it's so if we come up with a new framework in Node.js that does high performance, we say high performance computing, it should make the JavaScript application you write as fast as the native library of the Node.js API calls, right? You know, so that's so on the speed side, that's the only requirement that we have. However, on the other side, which is the software engineering side, there's lots of other requirements that the framework must be able to satisfy in order for developers to use it. Because in the end, I can, you know, if speed is all that matters, then I can write everything in C++, and people are not doing it, and people will not do it, because there's the native binary have all kinds of problems. We need other things, that's other benefits of software engineering that has happened in the past, say, 25 or 30 years since Java came along, right? You know, the safety and the security of the runtime, the portability of the software so that I can compile it on my Mac and then run on Linux, right? I don't need to have the exact same machine on my development environment and on the deployment environment. And I can move it around in different deployment environments. I can manage it. I can allocate resources to it, and I can tell, you know, I can say which resources it have access to and which is not. I can stop it. I can restart it. I can move it to another machine, all kinds of, all those things the IT folks would want. The new framework would need to be able to integrate with existing ecosystems. You can't have something that is brand new, because the learning curve of something like that could be really sharp, and it takes 10 years for, say, Ruby on Rails to get popular, right? And also for Node.js. So, so something to get a developer mindshare, you also need to have it to integrate with a large existing ecosystem. And it needs to have high developer productivity. We are looking to squeeze performance from the top, but it's not in the way that is crude, that is only optimized for the machine. And we also want to make it so that we preserve the software engineering gains that we achieved through the past 30 or 40 years, right? So that we want the way we do it is to native performance, but with all those nice features that managed languages or managed runtimes that give us. So that sounds like a wish list, right? And I think Node.js and Python have achieved some balance of it. That's precisely why they're successful. But I also mentioned their shortcoming is that if you write, they provide API for that, but they don't have a way they don't have the flexibility for developers to write, say, arbitrary JavaScript or Python applications and achieve the same performance as their native API provides. So what's our answer? Well, so the first thing we need to really think about is choosing a battle of programming languages, right? So if we want to write high performance application, like the science paper also alluded to, the software bloats start with our choice of programming languages. I frequently refer to C, C++ as the most efficient, but not for everyone, because of all this, the safety and the portability and other things that we described. And here is a table of the performance of different languages and the, in terms of execution time and the memory it takes for the runtime. And you see, some languages like Python, it's very, very slow, and Java takes a huge amount of memory at runtime. C, C++ is probably can be used as a benchmark. They are small and efficient. And what's the second column? It's Rust, right? Rust is a very popular programming language. It's it's popular as a C, C++ replacement because it provides a lot of the high-level programming language features to C and C++. It makes it far more productive to write safe code and secure code in Rust than in C++. And because of that, it is a fast-growing programming language, and it's also one of I think 5 years in a row, it's the most beloved programming language by the Stack Overflow survey. So I think Rust would be a pretty good language to choose to write high-performance applications that can run inside environments like Node.js. Would you agree? So that's my assessment. And if you don't agree, that's email me or get in touch, because this talking about which programming language is better is a holy war, right? Is that everybody has their own opinion. It's just my opinion. I like Rust. That's why I'm giving a talk here, right? So, however, how do we run Rust code on the web? So there's the old way. I think that's the predominant way that people do it now. Is to write it as a native module. So I create a web server that has a native module, right? This could be Node.js, it could be Apache, it could be a lot of things, and it's just write or have a web server that is written in Rust so that it can execute Rust application logic behind the HTTP interface, right? So there are a lot of projects done this way, and they have seen a huge performance gain over other approaches like Node.js using JavaScript, right? However, the problem with that is the problem we have mentioned. It has to run full native code. It's not friendly to the cloud providers. It's not even friendly to the IT department, because people cannot really audit the native code. And even if you are completely trustworthy yourself, you say, my code has no bugs and has no security problem whatsoever. But most of those code depend on third-party libraries, and those libraries might have problems. So running native code is always an issue for big organizations. So that's in my opinion, that's what hinders the adoption of Rust in big enterprise at this moment, right? Because the need to run things in native, and even with containers, it's not completely safe, and it has, it has all kinds of issues, which we can talk about in a minute. So a better way is really to compare it to a managed bytecode, the approach that Java has pioneered 20 years ago, right? So to compile it into a bytecode and run inside the managed VM, give it a lot of benefits. And this VM today, the leading choice of this VM is WebAssembly. So here's the co-founder of Docker. He said this last year, WebAssembly on the server is the future of computing. He even went on to say that if WebAssembly and what the WebAssembly system interface has existed in 2008, they would not have invented Docker. Right, that is how important it is. It's a new high-level container that allows us to run bytecodes that compiled from a highly efficient programming language. So that's something that we have not seen in a long time in computing in this industry. So I think that's what's most exciting about it. So the benefit of the WebAssembly VM, I think we have touched those points, many of those points early on in my slides. So the first, of course, is security, because provide a sandbox. It protects from yourself and protects from all the dependencies your application has, so that you don't have to run them at native. And it also provides something called capability-based security. It's a part of the manageability issue. It allows you, when you start up the VM, you can specify which file system directory it has access to, which environmental variables it has access to. So you can have an independent security policy that independent from the operating system itself, right? So security is a big draw for running Rust compiled high efficiency code in a WebAssembly VM. So, but of course, all this is not even an issue if it's not fast, right? So WebAssembly has to meet because we are talking about high performance computing, it has to meet the requirements that can run at close to native speed. So bytecode running in WebAssembly should be almost as fast as bytecode compiled to the machine binary. As we will see in a minute, that is actually true, which is maybe surprising to a lot of people. Of course, runtime safety is related to security, is to say when the application crashes, it should not affect other applications that are running in the same system. Docker gives you some of that, but we're going to talk about the problem with Docker in a minute. It's mostly related to performance. And the portability, platform independence is also a big draw, is that I can write my application on a development machine, and I can run Windows or Mac or whatever. And then this same application can be executed in a cloud provider. I don't even need to know what operating system the cloud provider is using and what standard libraries it has. Right? So its platform independence is a big draw. And the manageability, we just talk about that. It can be moved around. You can allocate a resource to it, and those nice features that the VM can give you. Okay, so here's a graph. That's a study that we did for WebAssembly, especially. We use the second state VM as the example versus Docker. So those are execution times. So the shorter the bar, the better, right? The shorter the bar, meaning the smaller amount of time it takes to accomplish the task. At the bottom two benchmarks, NOP and CatSync, are startup times and file system performance. One thing that really stands out is that Node.js isn't that bad. When compared with Docker native and Docker Node.js running the same application, Node.js is only about 100% time slower than the native application. That is of course because all those standard benchmarks are actually being optimized in Node.js. So if you just want to do number crunch, because those are essentially all number crunch. That's you are calculating the binary tree, 3-body problem, and things, n-body problem, and things like that. Those are number crunching, and those things are very heavily optimized in the Node.js V8 runtime. So they are, when the JavaScript runtime engine sees something like that, it actually knows how to build the very efficient machine native code to actually execute those. So that's why it's, I would say, in a realistic benchmark, the Node.js is going to be 10 times or maybe even 100 times slower than the native code if you run everything interpreted JavaScript mode. But because the benchmark is structured, it's actually not that bad. It's only twice as slow. So, but what's really surprising is in almost all cases, the WebAssembly runtime, meaning the bytecode, the Rust code compiled to bytecode and then run inside the safe sandbox VM, is actually faster than it's running in Docker plus native code. So I think many people challenge this result. We have shown this result to different people. That's we can talk about that in a minute. And people challenge this result to say, how is that possible? That doesn't sound possible because the machine code, even with Docker, because Docker adds very minimum overhead, the machine code should definitely be faster than running inside a sandbox. That is because the way the virtual machine technology has evolved over the past, I would say, 20 years, pioneered by Java, is the AOT compilation, the ahead of time compilation. So when the VM sees this WebAssembly bytecode, the first thing it does is to compile it to machine code and then run it. In the process of compiling to machine code, it can have many different optimization options that is not available when you compile it to Docker plus native. When you compile a Rust or C++ application to full native application, you actually get, you specify a set of compiler optimization flags that is fairly generic, that depend on your guess of the operating system, of the target system. So for instance, you're going to say it's an Intel processor, so it's a x86 processor and optimize for that, right? But for SSVM and WebAssembly knows exactly the type of machine it's running on. It knows it's an Intel processor or AMD processor. It knows how much memory it has. So it can intelligently choose the compilation flags that make it run faster. Because all this is done dynamic at runtime, not at the compile time anymore. The compile time, you just generate the intermediate bytecode, right? So that allows the WebAssembly to have even higher performance than native code. So that's one of our requirements is as fast as native machine code, right? But you can see from those benchmarks, the WebAssembly bytecode with the AOT compilation is actually better, in terms of compiled bytecode. That's a very surprising result. And because of this result that we wrote an article that is peer reviewed, that is already accepted for publication in IEEE software. It's going to come out this year. It's called the lightweight design for serverless function as a service. It compares the second state VM against leading serverless containers, including Docker, Amazon Firecracker, and the Google's gvisor plus Docker. So this is a research paper that's already peer reviewed and accepted. And if you want to a preprint of it, let me know, and I'll send you one. So that's the surprise result, is that WebAssembly provides safety and better performance. You don't have to compromise between safety, developer productivity against the native code performance. You can actually do both. So that's a big takeaway from this paper, and maybe from this talk as well. So I'll skip this. So let's look at the application architecture. That's a typical Rust WebAssembly-based application run inside Node.js, right? So on the front end, there will be the Node.js JavaScript runtime, and so developers can write things in JavaScript as they want to, because that's proven again and again. Developers want to write their application, most of their application in JavaScript, and when it comes in, the runtime figures out the what the application is actually doing. If the application is making Node.js function calls, it's typically dedicated to the C++ based module library, so that it can go on and get and execute it as native binary. But as we said, the native binary is all nice if it's audited and if it's safe, but a lot of them are not, unless it's come prepackaged with Node.js. To install third-party native libraries is always a challenge. So for the other computational intensive tasks, it could optionally route it into a WebAssembly runtime and run it inside WebAssembly and get the result returned back to JavaScript. So for instance, this could be it could be a complete task of image recognition or face recognition. So the Node.js runtime just pass the image and the model to the WebAssembly runtime, and it would do file system access, access the GPU, and do all that stuff, do all that magic. And this particular WebAssembly virtual machine code is compiled from a Rust program. So for developers, they write two pieces of software. One is the JavaScript application that handles the web-related stuff. And then the JavaScript application calls APIs. Part of the API is the Rust application the developer has written and compiled to WebAssembly. So we're going to show a very concrete example in a minute. So let's just, and there's also a link. If you are interested, you can go to that website and see, that's how exactly different components of this system can work together. All right. So now let's look at the demo. That's AI as a service. Go to this website, secondstate.io/fast. What is fast? It's not fast, it's fast. It's a function as a service. It's a WebAssembly based function as a service. So let me switch my screen share to this website. Okay. All right, so here we go. So that's the web page. It's our, it has demo spotlight and scroll all the way down. It has a lot of tutorials and code, which we're going to see as an example in a minute. So let's go to do face recognition. It goes to an application that we wrote to say detect faces. And this application, I think it represents the future, meaning it is a completely static application. There's no server here. It's just, you can put it anywhere in GitHub pages or any static, or even host it locally. And what it does is it make a request to a serverless function that the serverless function is written in WebAssembly, written in Rust and compiled to WebAssembly. And the serverless function would process the request in Ajax and then come back to this web page. So all you need is a service where you can deploy WebAssembly function and pay for each invocation. There's no need to stand up a server that's 24/7 to process report, to process image upload and all that stuff. So let's do how it works. So you choose a file, you choose an image, and of course you can do a lot more. And then you say find faces. What it does is that takes the image, makes a web services call. It goes to the fast, the function of the service. The function of the service executes the WebAssembly function and mark up, first detect all the faces on that image, and then draw those green boxes around each face, and then generate the return image and return the image back to our browser so that we can see the result. So this fully interactive application, it's available 24/7, but you don't need to start a server and pay for the server to make it available. Right, so you can come here and use it at any time, and we are, as a host of this service, I'm not paying anything. I'm only paying for each request, right? So for all the time it's idle, it does not generate anything for me. So some of you might recognize, this is Nobel Prize season, and this is a 1927 Solvay conference. It's probably the most famous conference in the history of science. And there's 29 faces here. You may recognize some, most people would recognize Albert Einstein in here, but 19 of those people, 19 of the 29 people later got Nobel Prize, and some of them got twice, like, Madame Curie, she got it twice, right? So this is perhaps the greatest mind in modern history, and we submit an image, and the computer run a TensorFlow model and detect all the faces, and then come back. Very simple, and it spend most of the time uploading image and getting it back and rendered in the browser, right? That's the actual time to do image recognition on the server is under 1 second. It's it's a couple hundred milliseconds at this point, and we can optimize a lot more. But I just want to show you this example. And then let's see another example. Image classification, for instance. That's also another very popular TensorFlow model that I choose an image and I say, I already knew it's a dog, so I want to classify it, to see, it runs a TensorFlow model to say, it runs a TensorFlow model to try to detect what is on that image and then give the confidence of that, right? So in this case, it doesn't return an image back, it returns a JSON string. So it looks up its object classification table and said it's a pug, which it is, and it knows it has a very high confidence, right? So this whole process again on the server, it takes several milliseconds, and most of the time it takes is actually goes to get the image and submit to the server and then come back, and in all this time, I don't need to pay anything, as a service provider, I don't need to pay anything because I have no server. I just have a bunch of HTML, and then I have a function of the service sitting somewhere, and someone hits it, I'll pay a fraction of a cent to it, but I don't pay for all the idle time. So that's high performance computing plus the new billing model that gives us a lot of flexibility, right? So let's go back to our slide. All right, here we go. So we have just seen an example of AI as a service. I welcome you to go to that website and play it with yourself, and then see all the source code. It's all on GitHub, that you can see all of them, and then see how, But we'll walk through one of the source code in the remainder of this talk, so that you know how it works. This is the demo. And the architecture of this thing is, we have just described the overall architecture, but let me dive a little deeper into it to see how it works. So on the Node.js is a JavaScript app for the web, the network, and the database tasks. That's handled by function as a service. So that's out of the question here. So what we start is the Rust source code. It's the function itself. The function gets the input from the service, which is the image that the user uploaded, and it does all the heavy lifting of the image processing. Resize it to the right mount, to the right size, select the TensorFlow model, and pass the image and TensorFlow model to TensorFlow, and then after the result come back, it does the things like drawing the boxes around faces, and then generates the JSON and makes sense what the result is, and then get the result back. So it's the heavy lifting is all done in the Rust source code, and it's compiled into WebAssembly and executed in WebAssembly. And then the actual TensorFlow work is actually done through an interface called what we call the TensorFlow WASI, or the AI WASI system interface. So because this is fairly standard system command that requires the full native functionality, it's not, it doesn't really make sense to run inside WebAssembly because it's so standard, right? That's there's very little chance that anyone would be able to make it unsafe, or that's so all the benefit of WebAssembly is not here, but to make a standard interface in the Rust API so that developer can call TensorFlow has tremendous value for developer productivity, right? So we have a native wrapper of the TensorFlow command that can be invoked from WebAssembly. So WebAssembly runs on the server, runs inside the function as a service that it's process all the application logic. That when it encounters the task that needs to do TensorFlow, it passes off to the native command. Native command execute that and returns back into WebAssembly. WebAssembly process all this again and then return back to Node.js and then give it back to us. So that's the whole process of the application. So the Node.js code, again, it's very simple. It's just to take the image and return it. And what's important is the Rust and WebAssembly code. And as we see, this is meat of the application. This is why you need to write application logic in Rust and WebAssembly, because each of these steps is going to be very slow if you just write them in JavaScript. And so the first is you load the image that the user has uploaded, and you resize it to the model that TensorFlow demands, right? So for image recognition, TensorFlow demands 224 by 224 image size with RPG values for each pixel. So you resize whatever the format you get the image from, the JPG, JPEG, or PNG, or whatever. You normalize it and format it into that particular format the TensorFlow can accept. And then you load the model data. You select which TensorFlow model you want to run against this model, this particular image, right? Is that face detection, or is that face recognition, or is that object detection? So you choose the model data and choose the data that is associated with the model. So for instance, in this particular example, it's object classification. But all TensorFlow give back numbers, and you have to map the number into the actual words for the object, like a dog or a cat or uniform or whatever. So that's so you need a label file, and we read the label file that go with the model here as well. Then step number 4 is to actually execute the TensorFlow model, which we're going to talk about in the next slide. And once we execute the TensorFlow model, it gives back a bunch of numbers. It gives back an array of tensors, right? So that's what tensor is. That's a fun fact. That's the tensor was popularized by Albert Einstein, which we saw in last picture, because he needs that for general relativity. So now we are using TensorFlow to recognize a picture of Albert Einstein. So that's, well, anyway, just something I thought it'd be interesting to mention. So in number 5, we have the command return value as floating numbers, and then we look up the table to map those numbers and the probabilities into the objects or the images that they have. If we do face recognition, we would load the image again and draw those circles using Rust and WebAssembly to do it in a way that is high performance, much high performance than any JavaScript library can ever achieve, and then send the result back to us. So that is what we call, in our way of doing that, what we call high performance function. It's a function that's written in Rust and compiled to WebAssembly so that it can run at full native speed. And it's have access to the operating system or to other system resources that can make it run even faster, right? That's, for instance, in TensorFlow, we don't have to rewrite TensorFlow in Rust. We just make a system call from the WebAssembly runtime that shows how flexible the WebAssembly runtime is. On one end, it integrates with JavaScript. On the other end, it integrates with the native operating system. So number 4, step number 4 we left out is what we call WASI for TensorFlow. WASI is, WebAssembly system interface. It's commonly defined as how to use WebAssembly to access system resources like the file system, the sockets, random number generator, the clock, and things like that. But we can use WASI to access any command that's available on the system. In this case, we have the system installed TensorFlow command, so we use WASI to access this command. By having WebAssembly security, we can actually, at the time of, when we initialize the WebAssembly runtime, we can say which command you have access to. so that it has no unpredicted behavior. Maybe this particular maybe this particular instance can only have a particular kind of TensorFlow model, and not others. That we can specify this or when we start out the WebAssembly runtime. So that's why we say WebAssembly is more secure and more manageable than native applications. Right, here's an example right here. So to execute this TensorFlow model via command, we specify which model, which family of model it is. We just selected a model file, right? But we also need to tell it what's the structure of the model, and so there's different commands for that. And in this particular case, it's MobileNet version 2. And then we give it arguments. So the input, so the tensor name in this model for the input argument is called input, and the argument for the output is softmax. And the size of the image that the model expects is 224 by 224. And after that, we load the model data and the image data into the command so that the command runs the model against the image. So the actual execution of this command is actually in one line. It's command.output. It calls the command to WASI. And then the results come back, and we package the result into a JSON string, and then we have the Rust and the WebAssembly application continues to process this and return this value. So that's the whole application. The application is just a single function that's written in Rust and does most of the work in compiled WebAssembly. But when it does need the help from the operating system or from the system installed command like TensorFlow, it calls out through a well-defined and can be a well-defined interface that can be secured. So that's our application. So as you can see, that's one of the work that we do is that we try to make as many types of TensorFlow models available in our ecosystem, right? So this is all open source. So there's many family of TensorFlow models that we can incorporate into as Rust APIs, right? We just have shown you there's a MobileNet Rust API that calls the MobileNet family of TensorFlow models, and the MobileNet family of TensorFlow models has, I think hundreds, not thousands of models that people train, to recognize different things. You can have a model that very specifically to recognize different type of dogs, or you have a model that recognize different objects on your desk, something like that, right? So there's a lot of ways that you can have different models, and so we would like to have a open source project like the TensorFlow model loop, but it's TensorFlow model loop for WebAssembly, right? So to have those models being pre-packaged and made available through open source project, so that anyone that using Rust and WebAssembly to write those high performance applications would be able to use those models by just installing them through their compiler. So that's if you are interested in this initiative, you can go to the link here. It's second state AI as a service native model loop. So here are some resources to get you started. There's a guide, there's tutorials and documentation, and there's again, this is a link to the FAST. So that's it. Thank you very much for attending my talk, and I hope I'll see you in the community. Reach out to me if you have questions, comments, or want to criticize our approach. We welcome all comments, and just go to our website and find our contact information. Thank you very much. I'll talk to you later.